Today, Doctor. So we are from Group 4, and our design of experiment title is Fluid Projectile Motion. So our member consists of Tan Bing Jie, Ling Chang Yao, me, Anthony, Andrew Lee Han Hui, and Li Jing. Okay, so for the introduction, quality is actually incorporate quality into the real life product and process. So by setting up the specification for the acceptable values and also the allowable range for the deviation. So in this project, we focus on the design of experiment of fluid projectile motion, and we apply 2 power 3 full factorial design technique to optimize the horizontal distance. So fluid projectile motion studies always involve a systematic examination of liquid or gas projectile. And by utilizing the 2 power 3 full factorial design method, we can explore more interactive effects of the 3 factors with 2 levels each of the factors. So by systematic adjusting the variables, the project aims to be understand their impacts on the horizontal distance and also discover the optimal combination of the factor for the maximum distance. So for the problem statement of this project is to determine the optimum parameter in terms of height, angle, and also the fluid density for maximizing the horizontal distance in fluid projectile motion. And next problem statement is to investigate the interaction of fluid density with height, angle, and angle on the horizontal distance. Also, review the interaction and dependency between the factors in the fluid projectile motion. Also, systematic change variable by using the full factorial design method. Also, the one of the problem statement. And last but not least is contribute the insight for optimizing the fluid projectile motion efficient and effective. So the objective will be understand and implement the design of experiment technique for the optimizing the horizontal distance of the fluid projectile motion. And the second objective is to determine the interaction between the factors. And the third objective is apply 2 power 3 full factorial design method into the experiment.
So for the methodology of this project, we'll start from finding a suitable design of experiment. Then we'll go for the literature review and we'll identify the factor and we will conduct the experiment. So the data collection and analysis will using the ANOVA and design expert, and we'll go to the optimization of output, and then regression model development, and then confirmatory experiment and error calculation. So for the procedure of this experiment, for the first step is the apparatus is set up as figure beside. Then the spray is filled with water. The density will act as the factor. Then the angle is set up as the desired angle. The height of the spray is set up as the desired height at initial height, and press the pump of spray until the end within 1 second. Then we will measure the distance between the furthest fluid can reach and the original position. And lastly, we will repeat the experiment and change the factor from step 2, 3, 4. So for the design of experiment is the 2 power 3 full factorial design with 2 center point and 3 replication. And the factors are height, projectile angle, fluid density, and the response is the horizontal distance. So for the actual value of coded factor, the first factor is height, which is the low value is 0.465 and the height is 0.585. The angle, the low is 0 degree and the height is 15 degree. And for the density, the low is 920 and the height is 1000. So for the data collection, for the experiment with the summation and mean of rows, this table includes the detailed measurement and statistical summary. The table is divided into columns that represent various factors and their respective level. The factor 1 is the height, the factor number 2 is the angle, and the third factor is density. The experimental setup includes 8 treatment combinations that vary this factor as well as 2 center points to improve experiment accuracy. Horizontal distance were measured in 3 replicates for each treatment combination, and the result will aggregate to produce total and mean values. The total distance is the sum of the three replicates, while the mean is the average of these values, giving a clear picture of the fluid's performance under each experimental condition. The inclusion of center points or intermediate levels the inclusion of center points or intermediate levels of the independent variables improve the reliability of the experimental result by reducing variability and provide a central reference for factor level.
This shows the unknown table with all factors including in this experiment. Based on this unknown table, all factor was included, which is main factor ABC and interaction factor AB, AC, BC, and ABC. So basically, based on this figure, can see that the factor AB, BC, and ABC is not significant affect the result. So to make the result more accurate, we need to exclude this interaction factor and recalculate again the unknown table. Next page. So this is the actual unknown table that only consider a significant factor, which the unknown table is only include main factor A, main factor B, and main factor C, and interaction factor of AC. So basically, you can see that the model is significant and the residual is not significant. So based on the comment on the design expert, the model F value of 171.9 imply the model is significant, and that the p value less than 0.05 indicate the model term are significant. And the lag fit of F value of 2.69 imply that there is a 5.92% chance that is lag of fit. F value this large could occur due to the noise. This is the fit statistic for our experiment. We can see that the adjusted R square and predicted R square is basically greater than 0.9. So our experiment is considered acceptable. This is the normal plot for our experiment. You can see that the point C, point AC, point B, and point A is deviated from the red line. This indicates that they are significant affect the response reach the horizontal distance. Next page. This is the Pareto plot for the t value for our experiment. We can see that the most highest t value is the factor C, and followed by factor B, for factor AC, ABBC, and ABC.
So this is the main effect plot of factor A, so corresponds to the graph of horizontal distance against the height. Based on this graph, it shows the height has a slightly negative effect on horizontal distance, and the increase in height will cause a decrease in the horizontal distance. Next slide. So this graph shows the main effect plot of factor B that corresponds to the graph of horizontal distance against the angle. So this graph shows the angle has a negative effect on the horizontal distance. The increase in the angle causes the decrease in horizontal distance. Next. This is the main effect plot for factor C, which corresponds to the graph of horizontal distance against the density. So this graph shows the density has the positive effect on the horizontal distance. The increase in density will cause increase in horizontal distance. Next. This is the interaction plot for factor AC, which corresponds to the graph of horizontal distance against height, with two plotted lines corresponding to two different densities. Based on this graph, it shows the two plotted lines have different gradient compared to each other. So the interaction effect of height and density significantly affect the horizontal distance. Next. So now I will explain about the regression model. This is the final equation in the terms of coded factor. So the equation in terms of coded factor can be used to make the prediction about the response for given level of each factor. The high level of factor coded as +1 and low level coded as -1. The coded equation is useful to identify the relative impact of the factors by comparing the factor coefficients. Next, this is the final equation in terms of actual factors. The equation in terms of actual factors is used to make the predictions about the response for the levels should be specified in original units for each factor, and this equation should not be used to determine the relative impact of each factor because the coefficients are scaled to accommodate the unit of each factor, and the intercept is at the center of the design space. So
for this part, I will explain about the optimal setting chosen for the model validation. So there are 81 solutions that generated by the design expert. So for the first 1, 2, 3 in sequence, we will take it directly from the first, second, and the third solution that generated by the design expert, and the last 2 solution will be randomly picked from the design expert. So the predicted horizontal distance will be calculated by using the regression model. So next, so here at this table for the left side, it shows the predicted horizontal distance, which is the solution that we obtained from the regression model, and the right side show the actual horizontal distance, which we obtained by experiment, and the percentage error at here is minimum 6.154 and maximum of 8.085. Next. So for the conclusion, the significant factor and interaction for fluid horizontal distance are factor A, B, C, and AC. The optimal setting are height, angle, and density. So the predicted maximum fluid horizontal distance is 1.035 meter, and the percentage error between the regression model prediction and the confirmatory experiment result range from a minimum of 6.154% to a maximum of 8.085%. That's all from us. Thank you.